In this video, we're going to talk about related rates. For related rates, we find the rate of change of one variable that is a function of another, where both variables are changing with respect to the same independent variable. Usually that independent variable is time. We do this using implicit differentiation, which you may recall is an application of the chain rule. So here's an example. A pebble is dropped into a pond and ripples form in concentric circles in the water. The radius increases at a constant rate of 3 feet per second. What is the rate of change of the area of the ripples with respect to the radius? How fast is the area changing 1 second after the pebble is dropped? How about 5 seconds after the pebble is dropped? So let's sort of just draw a picture to think about what's going on here. So we've got like this pebble has dropped in the water and plunked, and you kind of know what this looks like. As time increases, the ripples in the water continue to increase outward. So that's what we're talking about. And we see that one piece of information that we know is that the radius increases at a constant rate of 3 feet per second. So the radius of these concentric circles in the water is increasing at 3 feet per second. That's the rate of change of the radius. We'll call that dr dt. The rate of change of the radius is 3 feet per second. Now we're asked, how fast is the rate of change of the area of the ripples with respect to the radius? So we know that the area, these are concentric circles, the area of a circle is pi r squared. That's the area of a circle. So we know a relationship between these things. And what we're asking, we want to find dA dt, the rate of change of the area of these circles. We know dr dt, in this case that's constant. Dr dt is the rate of change of the radius, and these are both with respect to time t. Okay, so we have this formula for the area. Now we're going to take the derivative of both sides of this equation. We're going to take the derivative of a equals pi r squared, and we're going to take the derivative with respect to t, the independent variable, time. And that means that the derivative of a with respect to t is just dA dt. Pi is a constant, so it just stays there. The derivative of r squared with respect to t is, now we're using the chain rule. Again, r is a function of t. The radius changes with respect to time. So back when we did implicit differentiation, that means you take the derivative of r squared to r, and then multiply by the derivative of the inside, just like with the chain rule. So the derivative of pi r squared with respect to t is pi times 2 times r times dr dt. We know from the statement of the problem above that dr dt, the rate of change of the radius with respect to time, is 3 feet per second. And so we can plug this in to simplify a little bit. And that tells us that dA dt, the rate of change of area with respect to time, is pi times 2 times whatever the radius is at that time, times dr dt, that's 3 feet per second. And so we could simplify that. 2 times 3 is 6. Pi times the radius, feet per second. All right, so that is the first question. The first question asked, what is the rate of change of the area of these ripples with respect to the radius? And that is our first answer. Next, it asked about what happens at time t equals 1. Well, at time t equals 1, we have to figure out what is the radius equal to. And as we said, dr dt is 3 feet per second. So the radius at a particular time t is 3 feet per second times t is 1 second at time t equals 1. And so the radius at that time is 3 feet per second times 1 second. That's just 3 feet would be the radius at that point. And so that means that dA dt when t equals 1 would be 6 pi times the radius is 3 feet, times feet per second. So how much is the area changing at time t equals 1? It's 6 times 3 is 18 pi times feet, so feet squared per second. That is how fast the area is changing at t equals 1 second. What about when t is 5 seconds? So again, we could figure out the radius, and the radius is 3 feet per second times 5 seconds. And so at that point, the radius is 15 feet, is the radius of these concentric circles of ripples in the water. And so that means that dA dt at that time is 6 times pi times 15 feet times feet per second. The rate at which the area is changing is 6 times 15, that's 90 pi times feet squared per second. That is rate at which the area of these ripples is changing at t equals 5 seconds, 5 seconds after we dropped the pebble into the water. Here's a problem-solving strategy for solving related rates problems. First, I really encourage you to draw a picture and name all the variables and constants. Like I said, usually the independent variable will be time, and we'll assume that all variables are differentiable functions of t. We'll then write down all the numerical information that we have. In the example above, for example, we knew that dr dt was equal to 3 feet per second. The rate of change of the radius was 3 feet per second. We'll then write an equation that relates those variables together. You might need to combine equations or substitute in order to do this. And then we'll differentiate that function with respect to t, or that equation with respect to t. And we'll use known values to find whatever unknown rate we're looking for. So here's another example to try. An airplane is flying at an altitude of 6 miles on a flight path that will take it directly over a radar tracking station. If the distance between the plane and the radar tracking station is decreasing at a rate of 400 miles per hour when the plane is 10 miles from the radar tracking station, what is the speed of the plane? So I encourage you to pause at this point, try this out, draw a picture, and we'll talk about it together in a moment. Okay, so let's first draw a picture and name the variables and constants in this case. So we've got some radar tracking station somewhere, and then we have a plane flying very high in the air. So this is not to scale. The plane is flying 6 miles up in the air, so the height of the radar tracking station is like probably moot compared to that. So this is an altitude of 6 miles. And what are we asked for? So we are saying that if the distance between the plane and the radar tracking station is decreasing at a rate of 400 miles per hour when the plane is 10 miles from the radar tracking station. So we are interested in this distance between the plane and the radar tracking station. And we'll also let's call that some variable. Let's call that variable S. S is distance between plane and station, and all of this will be at a particular time, so at time t. What other distances might we be interested in? Well, anytime you see something that looks kind of like a right triangle, you might end up thinking Pythagorean theorem. So in this case, another distance that will be of interest is going to be the horizontal distance, x. So x could be the horizontal distance between the plane and the station at time t. And we know that the height, y, is always the same. So notice that we've also got this vertical distance that will be useful. So what else? So we've drawn a picture. We don't really have any, well, we have this constant height. And then we're asked in particular for what is the speed of the plane at this time? So what is the speed of this plane when the plane is 10 miles from the radar tracking station? So when s equals 10, what is dx dt? We're looking for the speed of the plane. How fast is the plane traveling? It's traveling at this constant altitude of 6 miles. And so the speed of the plane is not ds dt. It's not traveling in this direction, but it is traveling in the direction of x. So what is dx dt? So let's write down the information we have. We know that when s equals 10, ds dt is equal to 400 miles per hour. And what are we trying to find? We are trying to find dx dt. So now let's write an equation that relates these variables together, x and s. So we know from the Pythagorean theorem, so here we've got s, we've got x, we could either think of it this way or this way, it doesn't matter, and then we've got a constant height of 6 miles. So based on that, we know that s squared is equal to x squared plus 6 squared. That's just using the Pythagorean theorem. And so that means that s squared is equal to x squared plus 36. So now we can differentiate this with respect to t. Note that x and s are not constants. X and s are functions of t. They change as time changes. And so when we differentiate this equation above with respect to t, we can differentiate derivative of s squared is 2s times the derivative of the inside. Derivative of s with respect to t is just ds dt is equal to 2x times dx dt plus the derivative of 36 is 0 with respect to t. And now we could try to solve for what we're looking for. We want to find dx dt. So let's solve for dx dt. We could divide both equations by 2x to get dx dt alone on one side. Dx dt is 2 divided by 2 is just cancels. So s over x times ds dt is dx dt. So s over x times ds dt equals dx dt. So that is an equation that relates these variables as well as their rates of change together. So let's now use the values we know to find the unknown rate. So we were trying to find dx dt, find dx dt at a particular moment in time when s, the distance between the plane and the station, is 10, and we know that at that point as well, ds dt, this radar tracking station, is able to tell how fast the distance between the station and the plane are changing, was 400 miles per hour. Okay, so that means that dx dt at that particular moment in time is s, that's 10 over x, whatever that is, multiplied by 400 miles per hour. We still need to figure out what is x. So we can go back to our Pythagorean theorem. We know that we've got x is the horizontal distance between the plane and the station. We know s is 10 at that particular moment in time, and the height is always 6 miles. So at that particular moment, 10 squared, the hypotenuse squared, equals x squared plus 6 squared. And so that tells us that 100 is equal to x squared plus 36. And because this is a nicely constructed problem, we'll get a nice answer. 100 minus 36 is 64, equals x squared. And so that means that 8 is equal to x. We're just thinking about the positive value. So dx dt, the rate at which the speed of the plane is changing, not the speed of the plane, the position of the plane is changing, is equal to 10 over, at that moment in time, x is 8, and times 400 miles per hour. So that's the same thing as 5 over 4 times 400 miles per hour. 4's cancel. That tells us that dx dt is 500 miles per hour. So that is the speed of the plane. That is how much the position of the plane is changing at that moment in time. And so that's the speed of the plane at that moment in time.